And Susan, you can take it over.
Great. Thank you so much, Krishna. It's really been my pleasure to know and to work with you for all these years, and I very much appreciate the kind introduction. So today what I'm happy to talk to you about is some work that we've done in my group on characterization and also beneficial use applications for a variety of different types of fly ashes. And in particular today, what I'll focus on is ponded fly ash, so ash that has been disposed in the field for some period of time, as well as off specification ashes as well, and looking at ways to reuse these in productive ways. So first of all, I'd like to give acknowledgement to the folks here who've done the heavy lifting. These are my collaborators throughout this project: Dr. Norte Uboa, who's now a senior engineer with Southern Company, Dr. Zenya Worth, who is an assistant professor at Cal State Fullerton, and Dr. Hyunwook Chu, who is an assistant professor at Kyunghee University in Korea. All of these folks have been a joy to work with and have gathered the data that you'll see presented today. So I'm very grateful to these folks. So what we'll see here, when we look at the concept of fly ash and sustainable materials management, we know that ASCE gives us a definition of sustainability, right? And that's going to be a definition that is focused on environmental, economic, and social conditions. And essentially what our goal is here as engineers is to maintain and improve the quality of life indefinitely using the resources that we have. We don't want to degrade quantity or quality or availability of any of these resources from a natural, economic, or social perspective, right? So this is frequently known as the triple bottom line model of development. In addition to that, we know that one of the ways that we can promote sustainability is by beneficial use of waste materials. And when we look at the waste materials that we are dealing with, we know that these materials must provide some type of functional benefit to us, right? That's one of the ways we define beneficial use. We also know that those materials need to substitute and use for a virgin material. So what that does is it keeps us from excavating soil when we can substitute in a waste material that's available for use. In all of these cases, we have to meet relevant product specifications, right? Any regulations, design standards, all of those must be true as well. And then finally, we want to be careful about environmental release. So we want to make sure that whatever is being released or leached from our waste materials is comparable to or lower than what we see from analogous products made from without the waste material. So when we take a look at this and we go further into today, what I want to do is focus on coal combustion products. So you'll see me refer to those as CCPs. Essentially, these are the solid materials that result from coal combustion when we generate electricity. Okay, so typically we'll have a boiler here, we'll burn the coal, we'll gather that energy, and we will convert it into electricity. So these coal combustion products you'll see frequently referred to in practice include a wide range of materials which have very different properties. Flue gas desulfurization gypsum, for example, bottom ash, boiler slags. I'll talk a little bit in just a minute about what those applications are. But primarily what I want to focus on today is fly ash. So that's the lightweight material. We see millions, literally hundreds of millions of tons of fly ash having been disposed geologically in the United States and across the world. I'm also going to focus even more particularly on off-specification ashes. So these will include things like biomass ash, normal fly ash, coal fly ash, but which has a high organic content, and ponded fly ash as well. So here's the motivation, and here's what we want to do, what we want to think about. How do we increase sustainability by beneficially using these waste materials? We also need to be concerned about concrete demands in the future. We have to be able to supply enough fly ash in order to make concrete. And there are times in the United States right now where we're limited in that. Also, how do we effectively use these high organic content or off-specification ashes, right? So we have a variety of different sources. We can see them in the pictures here. For example, on the left-hand side, you see a pond of coal ash. So we just dispose these, let them sit and age over time. What can we do with that ash? In the middle, you see a picture of a full-scale biomass plant. So here, in this case, we produce an ash which is very different from what we would expect from a coal ash. And then on the right-hand side, you see concrete quality ash. So this is the concrete trucks will just drive straight up to the plant, collect the ash from the exit of the plant itself. So let's start with a couple of definitions here. What is fly ash? In particular, fly ash is the fine-grained particulate material that results from coal combustion. It is the ash that flies up the flue. We capture it by emissions controls, which have become more strict in the United States over the last few decades. So it's a very lightweight, low density material. It is an aluminosilicate. And when you think about fly ash, you'll see that we generally divide these into two primary categories. First of all is class F fly ash, which is a pozzolan. And we typically obtain, these are loose categories, but typically we obtain class F fly ash from bituminous or anthracite coal. We also have class C fly ash, which is a pozzolan and cementitious. So it's self-cementing properties in class C ash. And typically we get this ash from lignite or subbituminous coal. And what you'll see when you look at the pictures on the right-hand side are images of a fly ash that has a low carbon content in the top. And what you see in this image are these nice, beautiful cenospheres. These are what we want to use in concrete. These are made of aluminosilicates, and you can slice through them and do analytical chemistry to identify the atomistic scale of what's going on in these cenospheres. They increase the long-term strength of concrete. Some ashes are good for mitigating alkali silica reactions. And then they also improve the workability of concrete as well. So that's what we want. And when you look at these types of ashes with low carbon content, these have a great deal of commercial value. In the United States, generally we'll sell these for somewhere between $25 and $50 a ton, depending on where you are throughout the country. There are other ashes though, which you see down here in the lower corner. And in this case, I'm going to highlight a couple of particles in these lower ashes that you'll see there. These are organic carbon particles that were not combusted within the fly ash, within the electricity generating process. These cause us some issues. And what you'll see in the US, when you have carbon content which is too high, in fact, those ashes must be disposed. They can't go into concrete, which is the most common use of fly ash. So let's think a little bit now. What you saw previously on the last slide was coal fly ash. Let's take a look at what biomass fly ash is. So in contrast, you see the coal information here at the top. We've got it split into class C. Remember, the difference here is that C has some cementitious properties. And we make these definitions essentially based on properties within the ash. So for a class C fly ash, we're looking at a primary oxide content between 50 and 70%. We want, for use in concrete, we want a loss on ignition of less than 6%. Class F coal fly ash has a primary oxide content greater than 70%, but again, we have to keep that LOI or that organic content. It's not an exact measure of organic content, but it's a quick and dirty way to approximate it. We want to keep that less than 6%. So the difference in biomass fly ash is we're actually combusting wood. You'll see a lot of plants collect urban wood waste, like leftover pallets. Those go straight to biomass construction plants or biomass electricity plants. You'll also see a variety of other waste materials. So if you've got logging debris that can't be used for anything, those types of materials generally feed into biomass plants. These are different, right? So the biomass ash is going to have a very high alkali content. It'll have a low sulfur content. And you can imagine that the carbon content is going to vary substantially based on the input that we have from the biomass plants. In general, though, we can say that these ashes share some characteristics. So in most cases, fly ash is going to classify as a silt material. We have seen some ashes that do have a little bit of plasticity to them. Generally, we're going to have a specific gravity on the order of about 1.8 to 2.9. And this will be a function of what minerals are present in the ash itself. We've done some experimentation looking at conductivity as well, and you can see a conductivity on the order of their silt-sized particles of about 10 to the -5 centimeters per second.
सब कुछ आता है, बॉडी मसाज और ये सब करवा लें। शादी के पहले लोग करवाते हैं।
Sorry, there's volume
Yeah.
trouble?
No, I think somebody did not unmute it. So let me
Okay.
unmute it. Unmute. Yeah. Please, everyone, mute your mic, please. Yeah.
Okay, good. So let's take a look next at ponded ash, and let's take a look at what this is, because this is a little bit different from the other materials that come fresh from a combustion plant. Essentially what we do is we sluice fly ash into disposal impoundments. So in the United States, what that means is we'll take an existing waterway, we'll dam it up, we'll make an impoundment, we sluice the ash in, and we allow for gravity settling. So we get solid liquid separation over time. What happens though, when we allow these ashes to sit in especially hot, humid climates, is we start to see weathering of those phases. Right? So it's basically a weathered coal fly ash. Again, it's a silty-sized material. It's very similar in its properties, for the test that we've done, to unweathered class F coal fly ash. We do see variations in carbon content in terms of the loss on ignition and total organic carbon content, as well as the specific gravity. So down below, I've shown you some examples that we have here. You can see that we're getting LOIs that range from a low of about 3 to 15%, right? So remember, LOI is going to combust everything. TOC, which is looking more particularly at the organic carbon, you can see we're getting from about 1.5% up to about 12%. Specific gravity also ranges, right? From a low, in this case, you can see of a little bit over 2 up to 2.7. That's going to be a strong function of the mineral phases that are present in the ash. A lot of times you'll see that ash has iron oxides present in it. In fact, you can dip a magnet into the ash and you'll pull out the iron particles very clearly. And you can also see here that we have reasonably good numbers on the primary oxide contents from the weathered ash, and that's makes sense, right? Because we're allowing this to age over time. We're dissolving out a lot of the soluble components, leaving the aluminosilicate spheres in place. So when we think about this problem, what's going on here, right? What we see in the United States, and I'm sure worldwide, I've seen similar trends in other countries as well. The waste streams are increasingly complex. So in terms of the trends that we have for fly ash production, we see changes in the properties from what we used to understand their properties to be. We also have changing disposal practices. In the United States, we've had a couple of spectacular fly ash failures, which have generated very strong public outcry, as you would expect, based on the picture that you see here. This is the ash spill at the TVA Kingston plant. And as a result of some of these types of disasters, we have much more strict disposal practices in the United States. So essentially what that means is we're going back and re-engineering some of these disposal ponds and putting them into Subtitle D landfills. We also have more strict air regulations as well. So what that means is things that used to combust and go straight out the stack 50 years ago, we could burn everything up and just discharge it to the atmosphere. That's not happening nearly to the same extent anymore. So now we're lowering our combustion temperatures and we're retaining some of the things that we used to combust and release, and we retain those for geologic disposal. So what that means is we're looking at changes over time. And then finally, we also have quantity and supply issues. So there are parts of the United States which are supply limited. They cannot get enough ash in the summer in order to supply construction demand. And I'll show you right here why that is. If we look at the energy sources in the United States, you can see over time that we have made a shift away from coal, right, to natural gas. So essentially the level of our coal percentage that we use to create electricity has decreased substantially. And that's just because horizontal drilling has become more effective and it's made recovery of natural gas much more cost effective. So what we see with that, it's just a lot cheaper to burn natural gas. And so you'll see a lot of utilities are converting from coal-fired power plants to natural gas-fired power plants. We saw some failures in Texas recently during some very cold times here in the US of those natural gas plants, but it's still it's not a trend that's going to change. This trend will continue as we move forward in time. What we do think, and what I believe to be true, is that the United States is going to continue forward with a very diverse energy portfolio. And I think coal is going to remain a small percentage of that portfolio, given no major change in, say, battery technology over the next 20 years. So I think coal will continue to be about 10% of our energy source as we go forward, which means we're still generating fly ash. We're just not always generating it in the right place at the right time that it's needed. In particular, the transportation industry has had issues. So you can see here, AASHTO convened a subcommittee on materials, and they have a fly ash task force report, which is easily accessible on the web. And what you'll see here is that from the period of 2012 to 2016, 80% of US state DOTs said they had a fly ash supply issue. These states range from the West Coast to the East Coast. So it's a countrywide phenomena. There were shortages in both Class F and Class C fly ash. Some states had shortages in both. And it's not limited to DOTs. The Federal Aviation Administration and the US Army Corps of Engineers also have reported running into these ash shortages. So for us, what that means is we want to start thinking differently, right? If we're not producing enough fresh ash, let's take a look and see if there's other sources that we can mine and take advantage of. So in 2019, you'll see here that we generated 79 million tons of coal combustion products. Out of that, fly ash was 29 million tons. That's down from 38 million tons just a couple of years before. I am very interested to see what the 2020 numbers show as a result of the virus, right? With construction being down in some parts of the country, I'm curious to know what we'll see here in terms of beneficial use. Fly ash is attractive because we use it as a cement replacement. So 1 ton of fly ash will reduce about 0.8 tons of CO2 that's released due to cement manufacture. This is a huge benefit for us, right? We can take a waste product that we're already making, we can substitute it for cement, which is one of the really big bad guys in climate change, right? This is a tremendous benefit for us. We also use fly ash in other applications, some blended cements. We use it in some embankments and road bases, and we use it for waste stabilization. Another CCP that is commonly used is the flue gas desulfurization gypsum. So this is used for emissions control in the US. And what you'll see is it produces a very beautiful gypsum. And in fact, it's a huge source of what we use in drywall in houses and buildings in the US. So a lot of the gypsum that we generate at power plants goes straight into construction beneficial use. We also have bottom ash and boiler slag. Those are used in a variety of different applications you see here. But the encouraging thing about CCPs is that we have about 52% utilization. So that's half of the waste products that are going to construction or other types of applications. And we're saving that space in our landfills. We don't have to geologically dispose those materials. So let's think about what we know about these alternate materials that we want to understand and that we want to put to good use as well. That other 48%, essentially, what can we do with it? So let me show you kind of a pictorial guide to what we have in fly ash. So up here in the upper left-hand corner, what you see is a low carbon fly ash that comes from burning coal. So this is a nice, beautiful, you see this, the concrete maker will smile, right? What you want are these rounded cenospheres because they help with concrete workability. You can see cenospheres within this fractured cenosphere here as well too. So this is essentially what we see in an ash that's coming from a plant that has a high commercial viability. If we look over here on the right-hand side, what we see again is a coal fly ash, but in contrast, this is a high carbon content coal fly ash. You can see the cenospheres in the background, but what you see here in the center is a carbon phase, and that carbon phase has some cenospheres sorbed to it or connected to it. And it's essentially a problem for us because that carbon interferes with cement in a couple of different ways. We'll talk about that in just a minute. If you look down on the lower left-hand side, what you see here is an ash that we did some test burns with Southern Company in the United States. And you'll see here that we took the coal, which is pulverized, and we took the biomass, pulverized it as well. We combined those energy streams and then fed it into a full-scale power plant. And what you see is kind of a mixture between some of the organics and the cenospheres. So we've got some formation of cenospheres you see down here, but then we also have this residual wood content that you can see. Okay, so this is a very different structure than what you see up here in this image. This image, this is a very glassy carbon phase, essentially. Down here, you can see that this, in some cases, is a little bit amorphous, and it's got that residual wood structure. On the lower right-hand side, this picture that you see here is biomass ash. So this had no coal in the input. It's 100% wood or grassy plants. And you can see very clearly the wood structure that came through not completely combusted. So that's what normal ash would look like coming out of an electricity generating plant or a biomass, coal or biomass plants. In all of the cases, these organics are generally what we have to worry about, what we have to work around, because they're going to cause issues from a couple of different perspectives. Now let's look at ponded ash. So this is coal ash that has been disposed. These are from the southeastern United States, so it's a relatively warm and humid climate. And these ashes have been disposed somewhere between 5 and 30 years, something like that. And what I think you can see pretty clearly here is the aging and weathering effects that we're getting from these ashes. In some cases, we're getting cementation between the grains. You can see that we've got precipitation of additional mineral phases on the cenospheres that we have present as well. Some amorphous phases we've found within these ashes. You can see evidence of what looks like visual evidence of those too. The other thing that's interesting, if you look down here, you can see that we've got this meniscus that has dried out. These are SEM images, so the samples are dry. You can see that as the meniscus dried out, we precipitated additional mineral phases here in the lower right-hand corner, which are connecting particle to particle. So these ashes are different. They're different in their characteristics. They're different in practice. So what we want to think about is how can we best use these different ashes? In general, the particle size is on the order of the silt size that we would define in the United States, as you can see over here on the right-hand side. So these are coal fly ashes and co-fired fly ashes that range over there for less than 100 microns. On the left-hand side of this graph, what you see are 3 biomass ashes that we tested from smaller scale power plants. So these are things like power plants that will power a paper mill, for example, or cement production. So these aren't full scale, what we think of as traditional urban power plant generation. The important thing to take home here is that on the right-hand side of the graph, our ashes are on the order of silt size. If you look over here, our ash particles are much larger. So let's take a look about what that means for us and what we're going to do with it. In terms of the physical characteristics, if we look at the residual organic carbon content, that's what ROC is telling us here in this upper graph, we can have organic carbon contents almost as high as 100% in some of these biomass ashes. So what that means is that we're not combusting the ash completely. We're not getting the full energy content out, or combusting the wood, I'm sorry, completely. We're not utilizing the full energy content in these cases. You can see for most coal and co-fired ashes, our residual organic content is going to be somewhere around 20% or lower. What we'll see though, right, is that when we're in these if we zoom in and we look in these regions here for the coal and the co-fired ash, is that we get a nice relatively linear relationship between our residual organic content and our specific gravity, right, which is what we would expect, right? So our organics are going to have a specific gravity of about 1. Our silica particles, which you'll see a lot of times in ashes because they come in from the boiler, they come in from the mining and the excavation, they come in from the storage lot. We know that has a specific gravity of 2.65. So we see this nice correlation as we do a mixture between the organic and the mineral phase components. The other thing that's intriguing to us and that we were interested in from a sorption perspective is you'll see that as we come in and we look at these biomass ashes that we have tested, we start to get into very large surface areas, right? So down here, you can see that we've got a biomass ash sample that had a surface area of about 700 meters squared per gram. And that's on the order of activated carbon, right? And that's quite remarkable. It's not too surprising that that's the case, right? Because we'll see that coal and wood and other types of natural materials, that's what we combust to make activated carbon. So it makes sense that the materials going through this energy generation, electricity generation process are going to have some similarities with activated carbon. When we look at this, we'll see again that we don't get quite as good a correlation, but our surface area is related to organic content, let's say. We'll show you a little bit more detail on what that means or what that says for us. One thing that we did was we wanted to understand where the organic carbon was occurring in our ashes, because organic carbon is the problem child. We wanted to remove it if we could do that cheaply. So we ran a series of sieve tests where we separated out the particle sizes, and then we analyzed how much carbon was in each particle size. And so what you see here down at the bottom is the residual organic carbon content as a function of sieve opening size here. So the black line is telling you this was a pure coal fly ash. The light green line was for a co-fired biomass coal ash. And then the bright green is a biomass ash completely. Okay, and so what you'll see there is that the larger the particle size, the higher the organic content. So what that means is if we can do a sieve separation, which is unfortunately energy intensive, but if we can do that, we can separate out a great deal of the organic carbon that's present in our ashes. So we can do mechanical separation, we know that. The other thing that is significant here, though, is those large organic particles have significant internal porosity. And so what that means is that when we measure the surface area, which is this right-hand axis here, when we measure the surface area, most of that high surface area that's present in the biomass ashes is bound up in the large particle sizes because it's internal porosity, right? As we get here to the smaller and smaller sieve opening sizes, we come down to those nice uniform aluminosilicate cenospheres. And so we see actually decreasing surface area with decreasing particle size, right? Which is a little counterintuitive from what we would think of as geotechnical engineers. But it's all due to that internal porosity of the organic particles themselves. We have also come in and done some things where we looked at some of the engineering properties of the ash stiffness. So in particular, you can see here that we have the small strain modulus measured as a function of organic content. So we start up here in our dark closed squares. In this case, we have an organic content of 1.1%. And as we go lower here, you'll see that as we increase our organic content, right, we're increasing our void ratio. It's a little bit hard to control the void ratio with this significant amount of internal porosity. But what also happens simultaneously is that we get a decrease in stiffness, right? We'll see that as well. We've done other properties too. We've done some work where we measured electrical conductivity as a function of organic content as well as a surrogate for moisture content. So let's think about what this means for us, because now we have very strict standards in the United States for what type of ash can go into concrete. ASTM C618 governs what goes into concrete, and I believe these are changing. These rules are starting to loosen up a little bit, but in the United States, ash in concrete has to be completely from coal firing. Okay, so we can't have other materials present in there. As we're starting to loosen these standards, people are looking at biomass ash and allowing that into concrete as well, or co-fired ash too. But the take-home message that I want you to see here in this case, we gathered lots and lots, I don't remember, but lots and lots of data points from the literature where we looked at the oxide content of a variety of different ashes that we're dealing with. So the purple diamonds that you see there are coal from the literature. The squares, the gray squares that you see here are our coal results, and then co-fired results in the green diamond or green triangles. And then you can see biomass over here. right? The biomass ash stands out from all of these other properties, right? And as you would expect in the biomass ash, we see a very high calcium oxide content, right, on the order of 30% in one of the samples that we tested. And then we see a very high loss on ignition. One of our samples was close to 100%, right? That's quite remarkable, meaning that we burned up very little of the organic content when that went through the power plant. When we look at this, one other thing that I want to point out is that the type of plant that is generating electricity is really important on the ash that is produced. Okay, so what we've got here are the first three examples, BP 1, 2, and 3, are power plants that burned biomass, but they were small scale power plants. So this is what I mentioned before, the paper mill, for example, used biomass as its input. BP4 is a full-scale power plant that is actually generating electricity for consumer consumption, right? So it's selling out. It's a as-needed addition to the power grid. And you can see that the values for BP4, the biomass plant 4, are substantially different than what we see in the smaller scale plant. So the other thing that's really critical when we're thinking about ashes is to understand the combustion conditions that produce the ash, because we'll see substantial differences depending on those conditions. When we're looking at ash, you'll also see that we're always going to come down and classify them according to class C or to class F ash. And what I've shown you here now are the results of our biomass ash and our ponded ash compared to some other pieces of data that we have, or some other sorting that we have as well. So the ponded ashes that we have tested, you can see generally are classifying as class Fs, the class F ashes. Those are the open diamonds that you see in these 4 different graphs here. So in all cases, for the oxide content shown here, and then as well for the LOI, you can see that we're in the reasonable range for a lot of these ponded ashes of what we would expect for a coal fly ash. Biomass kind of is a different creature, I'll say, in some cases. These in the green circle are the full-scale biomass ash plant that we tested. So those ashes are somewhere on the border between a C and an F ash. If the input is completely combusted or almost completely combusted, we can get reasonably low values of LOI for these ashes as well. So let's take a look at what we can do with it, right? At the end of the day, as engineers, we want to put these ashes to work so we don't have to geologically dispose of them. For us, one of the issues that we've had to deal with is in the United States, we're converting our power plants to low NOx, SOx, and CO2 operations, right? So what that means is that we're going to have a residual material which has increased carbon content, and that's detrimental in concrete. So in concrete, we want to use, in many concretes, I should say, we want to use air entraining agents in order to create air bubbles. We put surfactants in to create that air liquid interface here. And those air entraining agents are, the whole purpose is to make stable voids in our concrete. What happens when we have a high organic content, though, is that those particles, those organic particles, will sorb the surfactants. And what we'll see there is we have to add more air entraining agents, which are expensive. So it's costly to us. And so that's one of the reasons why we want to avoid high carbon contents in our concrete. So we looked at some other applications as well. So in this case, what you'll see is we did some tests on fired brick production. And bricks are a really interesting field. It's one of the places where there's still a lot of art to the production. We found it to be a very collaborative environment, interestingly enough. So brick makers see their competition as other types of construction materials. So they were very happy to work with us, give us the secrets of their trade and see what we could produce, essentially. And what we did in this example is we tested a variety of different off-spec ashes. So we had high carbon content fly ash. You can see the black nature here that's telling you we got a lot of organic carbon in there. We tested some of the co-fired ashes, some of the pure biomass ashes, and then we also worked with dredge sediments that we obtained from the Savannah Harbor here in Georgia. And then we also used commercial clay as well to make a variety of different mix designs and test the ability of these bricks to withstand weathering. So you can see here we tested a range of mix designs, and this is like a recipe where we've got some component of sand. We mixed in our off-spec ashes, we mixed in the dredge sediment, and then we mixed in clay, so normal brick clay. And you can see we tested a range of volumes here, along with some different water contents as well. And it turns out we made really great bricks. Actually, they were really quite beautiful. They performed quite well. Interestingly enough, in the brick industry, there's a clink test, right? You take those two and you knock them together. You can hear that crystallinity when you're tapping them together. You can see in these cases that we've got a variety of different mixes here. This is co-fired ash for mix 11, performed quite well with the 10% content. Up in mix 7, we have the high carbon content fly ash, again, performed well. In mix 15, you see that discoloration on the side of the bricks. This is a process which is known as scumming, and it's essentially a precipitation of mineral phases on the sides of the brick. It's considered unattractive, and it's a lower quality brick just due to aesthetic purposes. That was a result of the high calcium oxide content in the biomass ash that we were dealing with. At the end of the day, though, we need to know about compressive strength, right? And when you look at this, what essentially we did was we took these bricks and we analyzed them for a series of different climate applications. And for a climate with negligible weathering, you'll see that all of our mixes passed. So everything that we mixed into the brick, we had no trouble with at all. In fact, we believe that we saw some benefit here from the high organic content in some cases, because that is an additional fuel source during the brick process, the brick making process. We again can look at increasing climate demands, right? And so as we look into a climate which is moderate weathering, and this is temperature based, you can see that we came in and eliminated some of the mixes, but we still retained quite a few of them as functional. And then when we get to severe weathering, we started to have more of the mixes drop off. We only had 6 or 7, I think, that retained enough compressive strength, or that exhibited enough compressive strength to withstand these more severe climates. The thing that's important here, though, is that these were bench scale tests. We were doing them in the laboratory. If we were doing these in a full scale kiln, we feel confident that we would have gotten better results. So these are conservative. So it's definitely a place where we can see these applications for these off specification ashes. We also, as we said before in the very beginning, we have to make sure that we're not leaching into the environment when we're using these different types of ashes. So we ran some T-clip tests. You can see here that we've got on the right-hand side, we've got our threshold conditions, and you can see that our bricks did not leach in substantial quantities. So we were fine as far as the environmental release goes. In addition to bricks, we've also done some work looking at geopolymerization. So this is a condensation reaction. And essentially what we do is we take an aluminosilicate material, we mix it with an alkaline solution, and we come through with a 2-stage reaction process. So we dissolve it, and then we precipitate it into a solid binder. So this is done these days, usually using a clay-based material like metakaolin. We can use it as a substitute for Portland cement and concrete. But what we can do is take some of these coal ashes that we're disposing, and we can use these as the source of aluminosilicate for these types of reactions. So what you'll see here is that we tested this not with the low carbon fly ash, but with biomass co-fired ash and with the high residual carbon content. And you'll see here the steps in the process. Essentially, we took these ashes and we combine it with the reagents of sodium hydroxide and sodium silicate. And then we've got a sodium hydroxide solution that we're going to dissolve them in. Okay, and so we mix them, we allow them to sit overnight. And what you'll see in that process is we start up the polymerization reaction that you'll see here. Okay, so we generate a precursor gel, we call it, and then that gel starts to form the backbone, and we get what we call condensation and hardening. We modeled, or we formed these into cubes, and then we came in after curing and tested those cubes for compressive strength. These are just some up-close images of what you'll see here for the different types of polymers or the different concentrations that we use. These are increasing concentrations of sodium hydroxide. And you can see here in this case that we've got the cenospheres in the background, right? But what has happened is we've dissolved quite a bit of this and gone through now and done a precipitation on top of that. So that's what the fuzziness essentially that you see in these pictures is. That increases as you can move down to the bottom right-hand corner. You can see with 3 moles of sodium hydroxide, we've done more extensive dissolution and precipitation in that case. These are up close, so we're getting into much, much more highly concentrated sodium hydroxide, 6 molar and 12 molar that you see in this case. We've got a cross section where we've cut through one of the cenospheres. And if we zoom in and take a closer look at that section there, you can see that we've got this precipitation coating, and we've got a variety of different dissolution precipitation processes that have taken place outside of the cenosphere itself. So it's dissolving and forming that matrix as well. You see something similar down here in this picture too. So what does this mean for us, right? At the end of the day, we're worried about compressive strength. Can we make these materials strong enough in order to perform as we need them to perform as a construction material? And what we did was, if you see the points circled in red, those are our reference tests. And you can see that we ran an experimental matrix where we tested the effect of the sodium hydroxide in the activator solution. Okay, so in the upper left-hand corner here, right? So at 6, right, we're looking at a compressive strength on the order of about 25 megapascals. If we increase that concentration, we're going to get higher compressive strength. Decrease it, we get lower compressive strength. The problem is, right, is that if we use a more highly concentrated sodium hydroxide solution, it's going to be more expensive. Similarly, if you see here on the upper right-hand side, right, we can increase the ratio in the sodium hydroxide to sodium silicate solution, and we see impacts on compressive strength as well. So the sweet spot there was at a ratio of 1 in this case. We did not see a substantial change in the ash to activator solution mass ratio here, or we also did not see a substantial change on the effect of temperature. So that was good news for us, right? We're trying to run these at low temperature, a relatively low temperature in order to keep the energy expenditures done. Always at the end of the day, anytime we're doing ash processing, we're increasing the energy input to the system, we're increasing the cost. And so that's a serious problem for us. So let's take a look at ponded ash. And this is the kind of the third category of ashes that I'm going to talk about today, ones that we've tested. So ponded ashes are different from what I've talked about so far because these do come from coal, but they are variable in their composition. So some ashes that are ponded were great fly ash, but it was produced in the off season. So there was not enough construction going on to use this ash, so they disposed of it in a pond. Some ponded ashes are high organic content or off specification ashes. And usually these two are mixed together in the electricity plant's disposal ponds. So you can't separate them out is the other part of the problem. They're also often co-disposed with a variety of other waste materials. So you'll often see bottom ash or slag disposed along with this ash. They are highly variable in age too, right? So you can layer, you can dig down layer by layer. We've got some ash ponds in the United States that are close to 100 years old. They've been through a series of cycling, so weathering through temperature cycling. They've been immersed in water. They've been exposed to the elements and microbial activity. They're not really well characterized as a pozzolan. So we wanted to understand their behavior and potential use. So we took samples, ponded ash samples from 3 different disposal facilities in the United States, southeastern United States. And we took samples from about 5 feet deep. So these were surface disposed, about 10 years old. And then we took samples up to 60 feet deep, right? So those, it's hard to estimate in power plants because the records aren't always perfect, but those were on the order of 30 to 35 years old. So At the end of the day, what we saw though is that these were weathered under a temperature range of between about 25 and 100 degrees Fahrenheit in a subhumid tropical climate. These are all ashes that were sluiced to the ash pond for permanent disposal, and they were sourced from eastern bituminous coal. You can see a range of different materials present in these ashes, and we'll talk in a little bit more detail about them. In this case, there's a lot of numbers on this, and then I don't want you to take a look at all those numbers, but the take-home message that I want you to see here is these ashes are really in good shape, right? So these have primary oxide contents that are 80% or higher in every case that we measured. We see specific gravities that are on the higher end than some of the other organic ashes that we saw, right? So that tells us that we have more of the solid mineral phases present. And then we see a range of LOIs, and that's the place where we want to come in and be careful here. So some of these ashes still had LOIs that were quite high. What is complicated here is that LOI is often used as a surrogate for organic matter, but in reality, LOI measures some other things as well too, and we'll talk about that in just a minute. Just a reminder here to show you that these ashes, in terms of their oxide content, and many of them in terms of their LOI, do meet our standards for ASTM C618 use in concrete. So that's the good news, right? A lot of these ashes have no problem whatsoever meeting those concrete requirements. So these are the ashes that we're going to talk about now. And what I want you to notice here, the reason why I bring this picture back up, is these surface coatings that we have on these ashes involve other mineral phases that have precipitated in place. And what we see when we've tested these ashes is that we get a large concentration or large quantity of hydrated mineral phases present in the ashes themselves. And that's going to be important for us when we think about reuse in concrete. So what you see here is SEM image on the right-hand side, and then we've got the EDS data on, or sorry, SEM on the left-hand side. We've got EDS on the right-hand side. So this is an image of a ponded ash, and these ashes themselves, we know have calcium sulfate precipitated on it. What you see is this map tells you where the oxygen is present on this sample. So the oxygen is shown here in blue. We've got iron shown in red, silica in yellow, and then we've got calcium, sulfur, and aluminum. You can see where all of those map to the image that we have on the left-hand side. So what that means is the places where we have calcium sulfate, right? We can overlay these two images here, and we can see where we're getting gypsum precipitated in these products. And that's part of those cementing bonds that we saw in the previous images themselves. I mentioned earlier that we have iron deposits usually in fly ash as well, usually a reasonable concentration of iron. And that's what you see in the red map here. So this sphere that we have here was actually a solid phase iron oxide. And then we've got iron precipitated on the surface of these as well, right? Not necessarily a problem so much, but it is something that we want to keep track of as well. When we look at what this means, right, and how we analyze these ashes to see if they are available or usable for concrete, we need to think about the LOI concentrations here. And what that means, or what we've done with that, is we've come in and we've combusted, we measured how much mass change we got as we ran these heating exercises. And what that tells us is we can take a look at the TOC versus the thermogravimetric measurements that we have. And what we see is that it's not just organic carbon that's present in these ashes. What we see is that we've got a lot of hydrated minerals that are burning off and that are being counted in that LOI number. So LOI is not a perfect surrogate. In general, the take-home message here is that weathered fly ashes are going to have lots of hydrated mineral phases, gypsum, portlandite, in comparison to unweathered fly ashes. And that means that their LOIs are not necessarily an issue. It's just increased presence of these other mineral phases. Okay, so we don't think LOI is directly corresponding to carbon content. In concrete, we also have to worry about the amorphous content, okay? And so we know that that's the surrogate for pozzolanic reactivity. And so we came in and we measured that amorphous content. You can see the silica hump that we have here using XRD. And in all of these cases for the ponded ash, we saw a reasonable amount of amorphous content too. So what that's going to tell us, right, when we come in and we test the strength of these ashes, is that we get reasonable performance in terms of the concrete that we made out of these ashes. Okay, 9 of the 13 ponded ashes met our C618 criteria. The ones that failed did have LOIs over 6%. In addition to that, the ones that failed, we still had sufficient strength if we gave longer curing time, or if we beneficiated using a little bit of metakaolin as well too. So there was hope for these other ashes. So let's take a look at this. So essentially what this means is we can come down and look at the ash source, right? So if we have coal ash with low carbon content, we want to put that in concrete. It's the best application. If we have coal ash with high carbon content, we can in some cases use that in concrete, but we have to be careful. We can use it in construction materials. We can use it in fired bricks. If we have coal ash that comes from ponded applications, we've seen success with that in concrete applications as well and other construction materials. And then finally, the biomass ash, we did not have great results with it in concrete. Okay, so we have done tests with it as a sorptive agent. We've used it as a construction material and then in fired bricks as well. So we have other applications that we can use those biomass ashes for. So with that, the take-home messages here I want to leave you with is that many of the off-spec ashes can be used and can be used well. Weathered ashes are going to give us a different LOI result than what we see in non-weathered ashes. And we know that we're going to see the big challenge with using some of these ponded ashes is the dewatering, getting all that water off because that's energy intensive. So with that, I'd like to thank our supporters, Southern Company and Georgia Power have given us a great deal of support as we work through this. Mr. Lamar Larimore, Hollis Walker, and Ben Gallagher have been close collaborators, so we're very thankful to them. This work is also done in collaboration with Daniel Benkesser, a student at Georgia Tech, Dr. Kim Curtis, and Dr. Chris Shearer as well. So with that, I'll thank you very much, and I'm happy to take questions.
Thank you so much, Dr. Burns, for your excellent presentation. So